Pranams to all for Teachers' Day and very happy Onam, Miladun Nabi. So we start our morning session. We're very happy to have Professor Clemency Montel, who's a historian of mathematics who explores the development and transmission of mathematical and astronomical ideas in ancient and medieval cultures. She has a PhD in mathematics from Brown University and is a professor at the School of Mathematics and Statistics at the University of Canterbury, New Zealand. Her work draws on both mathematical and philological expertise, particularly in the interpretation of scientific texts in Sanskrit, Greek, and Arabic. And her work has been recognized by awards like the Satish Bhatnagar Prize, the New Zealand Mathematics Society Research Prize, and she's deeply invested in educating people in the mathematical sciences and championing diversity and inclusivity in the mathematical sciences.
Thank you very much for that kind introduction, and it's a real pleasure to be here from New Zealand, indeed. So this talk from Aryabhatta to Bhaskara is a two-part talk, which I will share with my colleague Professor Ram Subramanian, and then followed up by Professor Mahesh to talk about Upapatti. Of course, probably for my esteemed audience, much of this is not new to you, but really just to showcase and celebrate the ingenuity and creativity of some of the scholars in the Indian tradition when it came to trigonometry. What I do want to do, though, true to the spirit of this conference, which is based on manuscripts and celebrating primary sources and their preservation and their care, is to try and champion the manuscripts of which the sources that we see give rise to. So, speaking of manuscripts, I'd like to start with a nod to where we're going to go at the end of this journey with a text that Professor Ram Subramanian will talk about. And this is a beautiful bound book which is deep in the collections of the Jaipur Palace City Library, which unfortunately is very tricky to access resources to, but I hope projects like Samhita will actually make these collections more celebrated and accessible to scholars. But anyway, when you open this up, there's this beautiful embellishment on the front and a title page on which you can open up. It has been well looked after, so you can see there's been some damage to the first folio of the manuscript, but it's been carefully preserved and fixed so more ripping doesn't happen. But after, in fact, this text is the Siddhanta Sindhu of Nityananda, which is where our journey on trigonometry will end. An astronomical work with an epoch of 1628. Nityananda, as we will see, was the court astronomer of Shah Jahan's court and wrote many monumental astronomical works. Incredibly so, despite the importance of this work, like many works in mathematical astronomy in India, this work is yet to be thoroughly analysed and brought to light, but hopefully with the more accessibility of manuscripts we'll see it. So after several pages with texts, one continues on, and you really can't see terribly well, but I might be able to zoom in on this. There are hundreds and hundreds of astronomical tables, beautifully and carefully transcribed. Of course, you can't see any of the numbers there, but the painstaking detail in which these have been transcribed, you can see page after page. So Siddhanta Sindhu literally means ocean of Siddhantas, and the PDF file is around 450 pages, each of which have these detailed astronomical tables. So even the act of copying this to produce a volume would have been an absolutely exceptional effort. And we do find that the mathematical functions that have been tabulated, as have the astronomical ones, are to a staggeringly impressive degree of precision here. So we're talking about a phenomenal astronomical work. But what I want to draw your attention to, I wonder if I can zoom up, let's have a look. Aha! Just to show you some of the detail that we've got here. So this is the first table of this monumental work, and it's a table, as we can see, let's see if we can go. Oops. Let's go down a wee bit. Oops. I seem to have lost everything. Hold on, let me go back. This table here, as it's called, Atta Kalaja koshtakaha. Koshtaka is a Sanskrit word for table. It can also mean a granary or a repository. And this is a table of signs, trigonometric signs, down to minutes of arc. So you can see here the way in which it's rearranged. If we go horizontally, we've got degrees, and if we go down, we've got minutes of arc. So there's a very clever way in which this table has been arranged. Not only that, but the degrees for the first quadrant have been given. That's enough to copy out. But by some very clever symmetries, you can see here they've managed to fill in the entire 360 degrees by this lovely handy table at the top for telling you, if you want the sign of something that's above and beyond the first quadrant. For those of you who will know a little bit about, you'll see there's the very famous sign of 1 degree here, which is where we'll go at the end of this journey. 1, 2, 49, 43, 11. Again, staggeringly precise degree, and there's some really interesting mathematics that goes behind producing this value here, which is to do with solving cubic equation, in fact. So a really phenomenal effort, and you can see not only does it go down to minutes of arc, but these red values here are the differences between successive values, which suggests that people may have wanted to use, or this table was intended to find yet more precise values of the sign to seconds of arc by using presumably linear interpolation between these values. Anyway, so that's where we're going to go. 5,400 entries were done, times 2, of course, if you take into account the differences. So we're talking about a prodigious amount of computation here, not only the copying, to be able to produce these values. So we ask ourselves the question, and I just want to highlight some beautiful synergy that wasn't even arranged, and that this work itself, you may have recognized it from looking at the exhibition last night, you'll find showcased in the conference document here, as well as in the exhibition here. So Siddhanta Sindhu, you can just see another little bit of a scope on some of the tables there. Again, you can just see with the level of detail that's going on, the real prodigious amount of mathematical effort that was undertaken. So it's absolutely lovely to see these manuscripts being showcased in this way. So where did this journey begin? Let's start where people might locate the beginning, the origins of trigonometry. As has been said over the last 24 hours, astronomers prior to the Indian civilization, of course, had alternatives for measuring chords in a circle. The Greeks famously had their somewhat cumbersome chord function where they could find, if they wanted to find something that was equivalent to the sign, they would have to find half the chord of double the arc. But very importantly and much more efficiently and computationally elegant, it was the Indians that had the insight to see the sign as to be this half chord of an angle which was inscribed in a right-angled triangle. And I think there's a lovely coin that was produced, a very, very costly one now, on Alexander's campaign with an Indian archer as well as an Indian elephant there, but really testifying to the incredible reputation of Indian civilization around their archery and their skill with the bow and the arrow. So this bow and arrow, of course, provided somewhat of a metaphorical, if nothing else, inspiration for astronomers to think about the terminology of the signs in ways which many of you know already. Whoops, let's just keep going. And that we can imagine the bow and the arrow. So let's have a little look at this more closely. The technical terminology relates entirely to the apparatus of an archer. So we look at the word for bow, which is chapa, which is this arc here, B, D, C. The bowstring, famously the jar, is the chord here, which is equivalent to B, E, C. And then half the bowstring, that is the sign, is jarda, but quite often this gets abbreviated to just a jar as well for the sign, just out of convenience. And interestingly, which hasn't been touched on so far today, cosine, of course, is a natural complement to the sign, but what was more understood was the shara, or the arrow, which is this little bit here, which is known as the versed sign, or the reversed sign here, this small arc here, it's a small line segment here, ED, which is the radius minus the cosine. So these were the two natural pairs from the earliest times. It's a much more intuitive way, as we all know, to think about trigonometry. When we teach trigonometry at schools, we teach them as ratios of opposite over, hypotenuse, opposite over adjacent, etc. This is really a much more intuitive way, in fact, asking the question, for a given arc, what is the line segment that is corresponding? So really, I think if we need to go back to trigonometry and teaching it, this is the way we should be going. Okay, so there's the apparatus for the name, and as we've seen, this fantastic etymological journey from the Sanskrit jya, or otherwise sometimes known as the alternative synonym jiva. Jiva was probably most certainly the word basis. V's and B's from Indo-European languages to Semitic languages are identical, and the dirgha, the long I, became its diphthong, equivalent diphthong in Arabic to al-jaib. Al-jaib, so this is a direct transliteration, if you like, letter for letter, but al-jaib actually already meant something in Arabic. It means it can be a geographical feature, a bay or a pocket or a fold or a cavity, among other things. Munjal likened it to a bosom, which is one of its sort of alternative meanings. And so when Western European scholars, Latin scholars, interacted with Arabic scholars, they took a direct, so you go from transliteration from the Sanskrit to the Arabic, but translation from the Arabic to the Latin. Latin sinus, just like your sinuses, that cavity or that hollow area which sometimes gets infected when you get a nasty cold, is the word and from which we get the sign. So this cavity, this hole, this area here. So really it's a beautiful historical story of cultural transmission originating from the beautiful Sanskrit word jiva for sign. So what's also a natural feature of trigonometry in India, is that we find it fully embedded in astronomy until rather late in Bhaskara. I think we could sort of pinpoint the time when trigonometry as a discipline starts to be slightly separated out. And that's because, so trigonometric functions, tables of trigonometry always generally appear in Siddhantas at the beginning of chapter 2, the Spashta chapter, because the orbital anomalies for planetary motion are based on signs. And so that's where you see it. So it's, for those who don't know much about the history of trigonometry, it's a very important point that it was fully a part of astronomy for many centuries before it branched out into its own abstract topic in its own regard. And going back to Nityananda and his other famous work, the Sarva Siddhanta Raja, has this lovely part of a verse. This is because he says, Yato Jakarta Atratagatho. This is because in astronomical models, the position of a planet lying at the tip of the half chord, situated perpendicular to the central line. So it's very directly applicable to astronomy. And of course, there are signs all over astronomy. So we see ascensional differences need a variety of signs, epicyclic corrections to planetary longitudes. Almost all topics in astronomy are utterly reliant on this function, which for a given arc, what is the corresponding line segment? Solar declination, another topic we've seen talked about in the last day, as well as zenith distances and the lengths of the shadow are all dependent on trigonometric functions, which explains its embeddedness within astronomy. An absolutely crucial tool, the central tool, along with perhaps Trairashika for the astronomer. And I probably won't dwell on this too long, but there's lovely metaphoric, a textile metaphor for sines and cosine that Bhaskara, who we will end with in my talk today before passing over, is this lovely verse here. Pato yata tan tubia urdvatiriak, it keeps going. Just as the fabric, patra, is made of warp and weft threads, so too the study of spherics is crisscrossed with sines and cosines. And so this is his introductory statement for his rationale for his jotpati, or his chapter which describes how to generate the signs. So before we have a look at some of the explorations and the creative solutions and inventions around sign tables and producing data. So practitioners who were astronomical needed to compute the half chords, and they did so by some really great geometry. Geometry will get you only so far though, and so the special value that we saw at the very beginning of this talk, the sine of 1 degree, is not able to be found directly geometrically, and so some real creative mathematics had to be developed to find that. But geometry will take you down, as we will see, to the sine of 3 degrees. Along with this came linear or occasionally some very ingenious second-order interpolation techniques to be able to find non-tabulated values to save practitioners from having to memorize and recite sines down to minutes of arc like we saw with Nityananda's table. And so now we'll just jump through in the second half of this talk by looking at some of the ingenious solutions to come up. So the very earliest approaches to trigonometry that we have, Viramahira's Panchasiddhantika, really just used some basic geometry to produce a sine table with 24 values. And of course, the first one that you always find is the sine of 30 degrees. And of course, my colleague here, Professor Mahesh, has noted that we're sitting in fact, a hexagon here, and so we could find the half chord of one of these lengths of these tables. So with the sine of 30 degrees, you can there happily jump and find the sine of 60 degrees by complementarity, the sine of 90 degrees, which is the radius, and by inscribing a square in a circle to be able to find the sine of 45 degrees. And then when you find when you throw in a few extra identities, such as this very important, and this was understood very early on, this half angle formula here, you can basically hop your way. Once you've got the sine of 30 degrees, you can find the sine of 15 degrees to 7.5 to 3 degrees 45 minutes, and likewise find the corresponding line segments or sines for those amounts there. So it's relatively simple to be able to produce your sine table of 24 values, and famously Viramahira's table in the Panchasiddhantika has a radius of 120. And as we all know, that the way in which these are codified was particularly ingenious. There's just one verse it takes to memorize your whole sine table, but there is something particularly beautiful and clever about the data storage, if we can anachronistically call it that, of these values. What happens here, for those of you that can read the Sanskrit, is the swara and the titiyaha, is that in fact Viramahira's verse goes through and gives you the minutes first. All right, so he gives 7, 15, 23, and so on, up to 60, and so on. And then he will continue on to give the corresponding seconds as well, and does so in various ingenious Buddha Sankhya terms, as well as other techniques as well. So really, in terms of, you could interpret this really interestingly. Perhaps you could consider the first 2 quarters of this verse, giving you a somewhat crude approximation to these sine values, and then you keep reading the verse to get the corresponding seconds there. So really what this is saying, interestingly enough, is that you do, suppose you wanted the fourth value of sine of 15 degrees, you actually have to read the entire verse, because the value does not come as a pair, but they're separate and disjoint. So it's a very clever technique to be able to compress and optimize the amount of material that you can encode in a very small space. It's a very interesting way of presenting tabular values, which is sort of abstracted away from the actual just articulating a versified table itself. At about the same time, Aryabhata's sine tables, and Aryabhata has some really interesting ways for finding sine values, 2 approaches, and this is a very famous verse, of course, which I'm not going to dare read in Sanskrit, but even my esteemed Sanskrit colleague, Maki, Baki, Paki, etc., can't say it without having a little chuckle. Needless to say, Aryabhata's suggestion for encoding words didn't really persist beyond his sphere of influence. And just delightfully so, notice again this lovely synergy and just the resonance that on the very front of your conference brochure here, you'll see a manuscript with Aryabhata's here. You'll see here Maki, Baki, Baki, etc., etc. And maybe it's because the Sanskrit was so difficult to pronounce, that the scribe has down the bottom, starting halfway through, realizing he's got to 13 and has run out of space, and then keeps continuing here, right, 14 and 15. We get here these sign values here. So they're inscribed in a graphical table as well as encoded in verse for easy reference. What's the important thing, as all of you know, is that these are not sign values themselves, but they are sign differences. And there may be, let's see if I can get this back, there may be reasons for this, such as that, of course, the actual values of these differences. Can I get on the next slide? Here we go. So we've got these sign differences here. So again, just like Varama, here are 24 values for arc multiples of 3 degrees 45 minutes. And their sign values. The radius here is 3,438, and I don't need to remind all of you that, of course, there's a lovely reason for that figure, is that it's almost like the modern day radian measure, which makes the units around the circumference and those along the diameter directly corresponding, with the result that you can get one bit of data here, that is the assumption that for very small arcs that the sign is equal to the arc itself. Aryabhata would have certainly used a geometric approach to computing his sign differences, but also had an ingenious recursive algorithm to produce successive sign differences, which we won't go in here, but it uses basically double differences in the ratio between them. I'll just have a wee highlight here that we also see defining signs recursively in the Paitamaha Siddhanta, the dating of which is relatively still not secure. But this, just have a wee quick look at this. Of course, it starts with the first sign is a 96th part of 21,600, and that's basically taking the 360 degrees of the circumference times by 60, so expressing it in minutes, and then dividing it into 4, and then again into 24 parts. So to get that very first sign to be 225 minutes of arc. And won't go into the details, but really just describes how to do that. So the first sign, of course, is 225 minutes, and the recursive formula can be generally stated as follows down below. This they'll be familiar to most of you in the room, with these double differences to produce the second one, 449, to produce the third one, and so forth and so on. And actually, if you keep going, you don't quite get to the 3,438. But it's almost certain that that's the radius that was imagined there. So we'll keep moving. So there's that sort of a recursive definition for generating signs, as well as a geometrical one. Brahmagupta too had his famous sign table in the Brahmasputa Siddhanta with his unusual radius of 3,270. His Khandakajika, though, produces a nice complement to a very long sign table, which is a beautiful half of an arya in which you can encode an entire sign table. Trimshat sanavara sendur jinatiti vishayaha. And then you've got your entire signs that you need. So, unlike his long one with 24 values in the Brahmasputa Siddhanta, this one has only 6. It can be expressed very compactly. And so it reads literally 30, Trimshat, increased by 9, Nava, 6, Rasa and Indu, 1, and 24, 15 and 5 are the sign differences, he says. And so we've got these sign differences, and we can add them all up. Of course, it's unexpressed, but of course the radius here, true to a karana, is a much smaller, easily arithmetically manipulable number of 150. And only arc multiples of 15 degrees. Now, when you only have a few sign values, of course, you need a good interpolation algorithm to be able to find precise non-tabulated signs. So the rest of that verse, for those of you that sharp and know it well, just gives a simple, again, beautifully, concisely expressed algorithm for linear interpolation to find these intermediate values. And true to karana, probably that was good enough if you need to do a quick sort of tabulation there. Just again, celebrating the manuscripts. Here's one from the Anandashrama Institute in Pune. Again, see this the inclination of scribes to grab up this tabular data. Here we go, trim shuts and avarasendur, etc. The scribe, alongside a table for declination, there's the 1440, has put these sign differences along here, and actually them themselves have put in the actual sign values along, again, probably for easy reference for these for the user. And just to say that all of these, while they give these sign values, don't give any explanation usually about how they were generated. And just, I won't dwell on it at all, but Amaraja, who was a very famous commentator on the Karna Kajuka, just for this very small verse, gives huge commentary going through in much detail how to generate each of these 6 signs and how to use them. It's really beautiful because he talks from the very beginning, and we actually get a sense and insight into the practice of how this might have been done by using ropes and nails, a flat piece of earth and a compass, and the various geometry that you need to do it. And you can read through his commentary, and really he takes great care to articulate step by step, and the detail that really stands in marked contrast to Brahmagupta's incredible succinctness at each of the generation of these signs. And so even putting strings across things and taking half of them and computing them. And of course, his method of computation doesn't follow the order of the signs. He first finds the sign of 30, then the sign of 60. He uses the verse sign, which is useful to find the sign of 15, and then to find the sign of 75 by, of course, these expressions of finding these chords and arcs and line segments in these circle. And then the sign of 45 is the very last one. And then he puts them all in order, and he gets his, and he takes the successive differences, of course, which have less significant figures again, so you can be even more concise in doing them. And so the interpolation algorithm, of course, is just a linear one. So sign of 24, for instance, you just linear interpolate between them to get 60.6. But Brahmagupta also includes this ingenious and very, very clever higher order interpolation, which is equivalent to Stirling's finite difference formula. If you look at it carefully, you can see the quadratic term there, in which you get an ever better approximation to the sign. So the less sign values that you have, the better interpolation you need if you're really wanting accuracy. So Brahmagupta is giving you, if you like, options depending on what level of accuracy that you want. And this was a really incredible feature of Indian practitioners, that they would give you multiple techniques depending on the level of accuracy you desired. So looking at balancing efficiency with accuracy in this way. Some of you will have heard Brahmagupta, you think, taking 6 values for your sign table via trim shuts and avarasendur genititi vishaya, which is very, very compact. Munjala comes in with the lagu manasa, which means, I guess, easy thinking, in 932, and has a sign table with 3 values here, which is just, taking optimization or efficiency to really its zenith. And so he says, the sum of each successive sign respectively, multiplied by 4, 3, and 1, considered as both degrees and minutes, determine the sign of the arc and its complement. So taking him literally 4, 3, and 1. So he's not even giving you the sign values, but really a very clever way for determining them. So even more compact and succinct, really demonstrating a poetic brilliance, if you like, about making this memorable. And, with a bit of head scratching, what he really means is that you take the first one, which is 4 degrees and 4 minutes. The second one is produced by taking the first one and adding 3 degrees and 3 minutes. And the third one, the sign of 90 degrees, which gives you your radius, is the second one plus this 1 degree and 1 minute, to get this quite unusual or distinctive value of the radius of 488 minutes. So really this is, I think, just incredible ingenious virtuosity on the part of Munjala to really explore and play with the mathematical features. Now, of course, with this only having 3 values for your sign, which is fine if you're an astronomer and just computing declinations for rashis, for instance. But if you want to interpolate or find a value that isn't 30, 60, or 90, again, you need a very precise or a very clever interpolation algorithm. Otherwise, it will be very blunt, very crude, that the non-tabulated values. Mallikarjuna Suri, much later, produces a very complicated algorithm, which would be fun to explore in more detail, but I won't do it here. And just jumping through, again, from brevity to a very clever rational approximation to the sign, which is the ratio of two quadratic functions here. And so subsequent authors avoid actually having to use tabulated values for trigonometric functions altogether and can just use this very slick algorithm in their formulations. We'll just touch upon that later on. But how this was derived has been generally understood by scholars. We don't have time to look at it here, but just to admire and remark upon the brilliance of this alternative to finding the sign to these tabulated values. And as you can see, it's incredibly precise, particularly for the values that generally you'll be using them for in astronomy. Bodhiraja. So we've looked at tabulated values that you memorize. We've looked at an algebraic approximation. Bodhiraja, we see the rise of graphical tables. And by I mean this, I don't mean versified tables, but tables that you write down. And this allows ever more increasing degrees of precision. So we have here the Svaraja Murganka of Bodhiraja in 1042. So it's very interesting manuscripts, characteristic of some of the ones in the British Library, which are these negative imprints. But you will see here, everybody's jumping, of course, tell me, to the very last value, which is the sine of 90 degrees, which has this wonderful radius of 1,000, which, of course, is very useful decimally. But, of course, nobody would memorize a table like this. You wouldn't commit a table like this to verse. So just to show the mediums in which people have available to them, dictates the mathematics and the precision and the shape of the mathematical function that you can have. Again, for some reason, he gives another sine table, which is just slightly different in ways that we haven't quite cracked or understood yet, followed by a table of the verse sign, the Kramajar down the bottom, for every 2 degrees. So this mode of expression, the actual tabular format, allowed people to experiment even further. And we see Bhaskara, which is where we're almost going to end this, improving sine tables yet again by extending the boundaries beyond just the 24 conventional values to a range of sine values. And I would say the Jotpati with Bhaskara, it's the time where we see sine and trigonometry exerted out of its fully astronomical context and treated as a subject in its own right. So you'll see Bhaskara's incredible achievement, as well as finding these sine of 18 and 36, which was generally well known, added this sum and difference formula in the form of a beautiful verse to produce a sine table of 30 values. And why do I say that? Because once you have the sine of 18 degrees and the sine of 15, you can take their difference to find the sine of 3 degrees. And that is the limit of the geometry to find integer degrees, the sines of integer degrees. Bhaskara also elaborates these very clever rules, again, as not necessarily for a practical reason for producing sines, but actually to investigate and explore the mathematical properties of the sine functions and ways in which you can generate further sines, given that you know one. So all of these are very interesting approximations which have been well studied. And the last one I want to really highlight before I pass it over to continue the journey is, despite all that incredible work for tabulating sines and finding ever more efficient ways or precise or accurate ways, is that by the time we get to Ganesha's Grahalagava, his particular distinctive contribution is to say, I'm going to show you how to do astronomy without even having to touch a sign ever. And his entire Grahalagava, this beautiful Mangala Charana here, which unfortunately we don't have time to look at, which you can read. It has a beautiful double meaning in it, but breaking the bow of Vishnu here means actually being able to compute astronomical handbook, a karana, which is devoid of arcs with their signs. And instead replaces it with these multipliers and divisors. So basically, he has recast all of these astronomical formula that we saw at the start by invoking algebraic approximations such as those by Bhaskara 1 to replace any practitioner having to consult a table of sines at all. So we go from sines being absolute, tabulated sines being the fundamental tool, to being able to avoid it altogether, really in a flourish of brilliance, to help, I guess, with the calculation and avoiding having to consult sign tables altogether. So there's a quick tour through the ingenuity and creativity and mathematical exploration of the sign values throughout the second half of the first millennium, and some of the brilliant insights and different modes of expression signs and the like. The balances that scholars had to take between precision versus memorability. There's sort of an optimization going on here between the two, and the brilliant interpolation algorithms that were used to be able to balance the ever more efficient way of expressing. Some of you, I haven't noticed, of course, in school will have learnt sine and cosine, and in the same breath have looked at the tangent function. It's another story in its own right. If I had another half an hour, we could talk about the ways in which we see the tangent function, which is directly correlated to the shadow, or chaya, of course, but is not seen in this context until much later as one of the trio of those three trigonometric functions. And so now with this, we've seen how we can geometrically get down to the sine of 3 degrees. Practitioners had to try different techniques again and use different sorts of ingenuity to be able to find greater levels of precision. And with that, I'm delighted to hand it over to my colleague.
So, invite Professor Ramasubramaniam. He will be speaking on From Bhaskara to Nityanand, Techniques for Evaluation of Signs in India.
Do you want to? I'm going to pull this out, shall I?
So, namaskar to all. So, I am going to continue the exploration in finding the sign values which had been done in India from around the 12th century to around 17th century. So, we had a brilliant presentation by Dr. Clemency Montel, so who just shared from early times till Bhaskara's time around 12th century, and she also touched upon Ganesh Devajna a little later. I would like to start with a very, very brief recap of what was done earlier, and then I will move on to one particular work. I will move on to one particular work, Siddhanta Raja. Siddhanta. So, this is done by Nityananda, who was a court astronomer in Shah Jahan's court, and then some interesting things that he has done which is not to be found in the earlier works. So, we will discuss all those things, and towards the end of the talk she was mentioning about sine of 1 degrees and how was it done. So, this will also be captured. So, this was a table which was shown by Dr. Clemency in her talk, and only one point which I would like to draw here is your attention is saikaje panchashat. See, he uses this. So, saikaje panchashat was a little confusing to me, and then saika panchashat aje. The word aja is used to refer to first Rashi. So, what he is trying to say is, I am listing out the values which are from 1 to 30 degrees. So, that is the thing that he is trying to bring out here. There are other interesting things about this verse which was sort of highlighted by Dr. Clemency in her talk. Okay, so what was the basis behind arriving at the sign table? So essentially it boils down to knowing only two mathematical principles. That is what we need to keep in mind. So one principle is you should know this Bhuja Koti Karna Nyaya. The other principle is you need to know the Trairashika. If these two things are known, Trairashika, even yesterday's talk, Dr. Aditya was mentioning, and even Manjul was mentioning during his talk, that this is to be considered as one of the most important things. And in fact, myself, Mahesh and Aditya, when we were studying, Bhaskara would go on to say that if you know Trairashika, the rule of three, then you can deal with all sorts of problems in mathematics. So that is how
Goes back to Vedanga Jyotisha.
Vedanga Jyotisha. Of course, the principle goes back to, but the declaration by Bhaskara is something which is amazing. So you know the entire mathematics if you know how to deal with Trairashika. Okay. Bhuja Koti Karna Nyaya. Very true. In fact, if these two things, of course, plus the square root principle is known, even you can derive the very, very complicated description which Aryabhata has given to find out the sign also. So which was highlighted by her. Okay. So this is something which I can skip now. So this also I will skip. I will come to this. So Bhaskara, till Bhaskara, she was trying to tell what was done earlier. And around 14th century, we find this verse quoted by Shankaravariyar in his commentaries Kriyakramakari and Yukti Deepika. Kriyakramakari is a commentary which he has written on Bhaskara's Leelavati, a detailed commentary, and Yukti Deepika is a commentary which he has written on Tantra Sangraha. Both are Sanskrit commentaries, elaborate commentaries by Shankaravariyar. So there we find this verse quoted, Vyase Varidhinihate Rupahrite Vyasasagarabhihate Trisharadi Vishamasankhya Bhaktam Rinam Swam Prathakramat Kuryat. So this describes basically this series. So yesterday we also saw during the exhibition, this was nicely presented there. So Trisharadi Vishama Sankhya Bhaktam. Tri Shara means 5. Vishama Sankhya refers to all the odd numbers. Bhaktam divided. So Bhaktam means devotee. Bhaktam is divided in mathematics. Okay. So Trisharadi Vishama Sankhya Bhaktam Rinam Swam. Rinam is minus, Swam is plus. This is an alternating series. This was even highlighted by Manjul Bhargava as one of the remarkable discoveries which has been made around 14th century. So this is the exact expression, first exact expression for pi. C by D is pi. So all of us know that this is the first normally attributed to Gregory and Leibniz, but 3 centuries before Madhava has given this verse. The other one related to sign. So I just showed this. So how they compactly put it, and you will see a little more complicated series which is also beautifully presented in just one verse. So the Nihatya Chapa Vargena Chapam Tattat Phalani Cha. So earlier presentation you saw the word Jiva refers to sign, and this Jiva, the expression is presented in this verse. Chapa refers to the arc of a circle. Chapa literally means bow. So in the context of mathematics, where we are dealing with periphery and diameter, the circumference and diameter, Chapa refers to the arc of a circle. Chapa Varga means a square. So Chapa Vargena Chapam Nihatya. Nihatya means you have to multiply. Then it says Tattat Phalani Cha Nihatya. Once again you have to do. So Tattat Phalani means you already obtained this. You once again multiply by r theta square. So Haret, you have to divide by what? Samula Yugvargaihi. The word Yuk refers to a even number. Oja refers to odd number. Yuk refers to even number. Yugvarga means the square of the even number. And then he says Samula. Samula, the Varga is considered as a mathematical operation. So a mathematical operation is performed with a certain basis, and that is what is called Mula. So 2 plus 2 square, 4 plus 4 square, Yugvargaihi. So this will give you basically this 3 factorial, 5 factorial and so on. So this is how the sine series is presented. So I am not going to show how it has been derived by these people, but I want to spend little more time about which many of us are not familiar, the work of Nityananda. So Nityananda, as I told you, was a brilliant astronomer in the Mughal court of Shah Jahan, and his period is, so roughly we understand this to be 1639. Now around the same period we have this Munishwara who came little later, so around 1646, he was also the court astronomer of Shah Jahan. So one thing which we find common in Nityananda's work as well as Munishwara's work is presenting the sine table for every 1 degree. Okay, so that is something which we find in their works. So his work he calls as Sarvasiddhanta Raja, and Sarvasiddhantanam Raja. Now, almost in a similar manner, Munishwara would call Siddhanta Sarvabhauma. Sarvabhauma is emperor. Here he calls as Raja. There he would call it as Sarvabhauma. Anyway, these are all interesting, important treatises. Sarvasiddhanta Raja is yet to be brought out, okay, in full form. Only one chapter, one of the Clemency student has done work on this. Okay. So this deals with a variety of topics, planetary computations, and incorporates certain Islamic parameters also, that is to be clearly ascertained. So we, as of now, that is the understanding that people have. So Nityananda has also, I think, she showed certain tables which he has produced. So how does the work go about? So there are 9 chapters. This part which deals with Ganita is yet to be studied by anybody. So it is still in the form of manuscripts. Whereas these are certain other interesting things which have been studied. And here this Nityananda, almost similar to Bhaskaracharya, he presents a verse. What is that verse? Without knowing the rationale behind, if you were to do mere astrology, etc., he criticizes. The verse is, Ratrau sadma vichitra chitra rachanam deepam vina kim yatha. Ratrau sadma. Sadma means a beautiful house which has been decorated. So if you enter into the house without deepa, what will you see there? Ratrau sadma vichitra chitra rachanam deepam vina kim yatha. Then deepam vina kim yatha. So there are 3 similes he brings in, almost a similar, that is one thing. And he would also say that all these things have to be studied by various astronomers who want to declare themselves as astronomers. So Kuttaka, this, that, etc., Tarka Shastra, so all that he will say. If you have not mastered all of them, then you are not eligible to enter into Siddhanta. Okay, if that qualification had to be laid, none of us can get into. So that is how he would just say, okay. So that is very interesting verse again we will have in this work. Okay. So then coming to the signs, so this is one of the elaborate treatments that we find among the mathematical treatment of signs. So in Aryabhatiya, we have essentially 3 verses, I would say, which are devoted to sign. 2 to present the formula and 1 to present the table. And when we come to Bhaskara, he has devoted around 20 verses particularly to deal with signs. And here, if you see, starting with 19 up to 80, we have more than 60 verses devoted to present the sign, okay, in great detail. So this is what he does. So 19 to, I'll just give you a flavor of a few verses, since many of us would not have occasion to read this. So that is the whole idea. And this is another interesting thing that we find in Nityananda's work is, so normally the commentators will come and say that this is why this verse is stated, but Nityananda himself seems to give the section breaks, okay, so what it deals with and so on. So he says at the beginning, Acharyavarya, this is the 19th verse, Acharyavarya ganakastayeva jananti yajyanayano papattim tato dhigantum padavincha tesham mahajado vanchati madrishopi. This is like Kalidasa saying, so I am alpa buddhi. So he says mahajadaha, he describes himself as mahajadaha. So Acharyavaryaha is an addressing word, Ganakaha. Ganakaha means mathematicians. Only those people can be considered as mathematicians who are able to explain the rationale behind the computation of science thoroughly. Tayeva jananti ye jnanayano upapattim. Jnanayanam means finding the sign. Upapatti means the rationale behind. So only they can be considered as mathematicians. Tato dhigantum padavincha tesham. So in order to consider myself as a mathematician to raise to that pedestal, so I am going to attempt to explain this. Mahajado. I don't think that can be done, but Ganakaha is the thrust here. They, he Acharyavaryaha, Ganakaha tayeva bhavanti. Because this doesn't really add to that. So in the Acharya is used in a general. In fact, I can say Acharyavarya. So of course that is true. And here, so having said this, he just goes on. Shashtyangulavyāsadalena vrittam. There is a very detailed description as to how you have to proceed, draw this and so on and so forth. These are all nicely integrated in the verse itself. Shashtyangulavyāsadalena vrittam digankitam bhumitale vidhaya pratyeka pade navatim lavanam vibhajyatulyam vilikhen manishi. So Shashtyangulavyāsadalena, Vyasa means diameter, Dala is half. So with the radius, choose that to be 60. So here he is just saying this is fairly large radius that he is talking about. Angula, even if you take roughly 1 inch. So he is thinking of 60 inches. I mean, if you just take that. Why is he doing that? He is doing this because he is going to ask us to mark not 24, mark 90 parts. So that is the idea. Shashtyangulavyāsadalena vrittam. Then he says digankitam. Digankitam means you have to just mark the 4 important directions in that. Bhumitale. That also says you have to choose a very flat surface. If you have to draw a circle with 5 feet radius, you have to ensure that the surface is absolutely flat. Vidhaya pratyeka pade. Pada here means quadrant. Navatim lavanam. Navati is 90. Vibhajyatulyaham. So ensure that they are equally spaced. So all that he presents. Then he moves on to say Navatyam shajiva bhavedvya sakhandam tadardham kharam shajiva nirukta tadardho nitam vistritrehe anghrivargat sapadat padam jashta chandramshakanam. So this chandramsha here refers to, see, Jya Ashta Chandra. So here 18 degrees. See, Amsha refers to degree. So Amsha in various contexts means various things. When we deal with sine table and other things, Amsha means degrees. So Jya Ashta Chandramshakanam. So this is something which we do not find in many works in the earlier period. So sine of 18 degrees he presents. Okay. A couple of other verses which are very easy to remember. Sine of, suppose you want to add sine of a plus b. You can say Anyonya Koti. So there we have another nyaya which we use in So anyonya koti maurvya gunite ye cheshta chapayor durje trijyo dhrite tayor yaha yogassa chapayogajya. These are written in nice Arya verses. So he has adopted, generally people choose Arya to give the rules. Even in the other mathematicians, you find Arya to give the mathematical rules, and they will use other beautiful meters to give you examples and so on. Okay, so this is what we find even in Ganita Kaumudi. So anyonya koti maurvya. So he just says, suppose you consider two angles, theta and phi. So you have to find so sin theta cos phi, cos theta sin phi. This is what essentially it means. Anyonya koti maurvya. So gunita. This maurvi. So the word maurvi, we need to understand. There could be confusion. Maurvi basically means jya. Okay, sine. Koti means cosine. So anyonya koti maurvya means sin theta cos phi, cos theta sin phi. Anyonyasya. Gunite, you have to multiply. Ishta chapayor durje trijyo dhrite, you have to divide by r. Yogaha means plus. Ah, exactly. That is this. See, jya essentially means string again. See, chapa, jya. That is why sine. So if you just take half of it, you get the sine. So that is the whole idea. In fact, we have no Maurvi Dhanushicha Tata Raghuvamsha. Okay, Kalidasa says. So it is just Maurvi Dhanushita. Anyway, so Trijyodhrite Tayor Yaha Yogaha Sa Chapayogajya. You see the same verse, you have basically the same numerator, only difference is minus. Therefore, he will say Viyutihi. Then Chapa Vivarajya. Okay, it nicely fits. So sin theta plus phi, sin theta minus phi. Okay. This is an interesting thing which I really enjoyed. In fact, this work was done when I went to New Zealand. So with Clemency, we were just looking into this manuscript, and we would have spent almost 15 days, okay, to clearly understand this about 80 verses. It was quite tough. Okay. This is a very beautiful, this is in Vamshastha Vritta, you see. How do we draw the circle? He says, Kakha gagham bhumi taleshu mandalam ngakendrakam karkatake nasadhayet kacham chacham chapayukam kangam changam kramad vyasadalatrayam likhet. A graphic description of how to draw the diagram. I'll just explain one verse to you, just to have a feel. He says, mandalam means circle. Bhumi taleshu, on a flat surface, draw a circle. Then how is the circle described? Kakha gagham. So we say, draw the line ABC, you say, right? Instead of ABC, he says kakha gagha. Okay, that is how it comes.
There are no diagrams ever drawn.
No, diagrams are also available in the manuscript. See, without drawing, so I don't think the teacher will explain. And sometimes the manuscript will incorporate them, sometimes they don't incorporate, as simple as that. In this particular manuscript, we find the diagrams also drawn. So, Kakha Gagham, you see? So, he's.
Later period, isn't it?
Which one?
Put the diagram in later periods. Not manuscript will contain.
Manuscript contains, I am not very sure when they would have started. That is a little difficult to say. So, of course, see what would have been. No, everybody writes. Everybody writes the description, but he is saying representation in the manuscript. See, that would have been possible because, see, later we find paper manuscripts. That is why it is possible. See, in the palm leaf to draw a diagram may not be so easy. Okay, or bitch bark for that matter. Okay, now I will just blow this up for you. So, what he is saying is, Nga Kendrakam. This is Nga. Kendra means center. So, you find Ka here, and then you will mark Ka 90 degrees. Ga you will mark on the other side. Gham. So ABCD is the circle. Kakha gagham bhumitaleshu mandalam nakendrakam. How do you draw the circle? Karkatake nasadhayet. Karkataka means compass. Okay. So Karkatake nasadhayet. Then he will say, see, chacham, kacham, chacham. See, you find the arcs to be considered as kacha and chacha. These are the two arcs. Huh? Yeah, I would have drawn this, but this was done for submitting in some manuscript. Okay, manuscript to some person. This, of course, we will do this. We should. So, kacham, chacham. Okay, kacha and chacha. Chapa yugam. These are the two chapas. Okay, this is one bow, this is another bow. Then he says kangam, changam, changam, kramat. See, these are the three radii you have to draw. Once you draw the circle, you understand? Kangam is one radius, changam is another radius, changam. Okay, so now you see the verse. See, kacham, chacham, chapa yugam, kangam, changam, changam, kramat, vyasadalatrayam likhed. Vyasadala is radius, three radii has to be drawn. And of course, the other thing goes, chacham, chacham, chapa yugas yadurjake, kange, change, lambavade vapatite. So, lambavade vapatite means, so how do you draw this? Again, a beautiful description. Lamba means basically a plumb line. So, what he says is, you have to choose this point, cha, and then drop a perpendicular. This is chaja, is a lamba. Chaja is a lamba which has to be dropped on kanga. Now, what is the other sign? So, sign of phi, suppose you want to find out, you have to take this cha and then drop a perpendicular to changa. So, that is what will be the sign for the other angle. Okay. So, that is what he is saying. So, the kange, change, lamba vade vapatite. Kachasya chapadvayayoga sammite. Now, what is your sign of theta plus phi? The sign of theta plus phi, he says, see, you have to just consider this cha. So, this So, sign of theta plus phi is cha ta. Okay, so this is what you need to determine. Okay, so how do you go about finding this? He gives a brilliant description of the whole thing. So, the geometrical description, how you can find out sign of theta plus phi. This is simple. After that, it is geometry. So, various things. So, he says, see, Ganaka Praveenaha. Okay, Praveena means one who is an expert. Okay, expert among the mathematicians. Sutram Jatakhyam Miliketa. The only one point that I want to draw your attention is, he uses the word Shilpa Siddham. The Shilpa was a little confusing for us. So, Shilpa normally means we understand the architecture and the sculptor and so on and so forth. Here he uses the word Shilpa. So, it is in a sense similar to that. You have to deal with the geometry in such a way and you have to cleverly find out the equivalence of two segments. So, Shilpena Siddham means, so here you can think of this to be a certain geometrical. So, even if you measure, you will be able to get this. So, it is in that sense he uses Tulya Pramanam Khalu Shilpa Siddham.
English construction. Laid and stone.
Pardon?
English word construction.
You can just say through construction you are saying. So, through geometrical construction essentially. Through geometrical construction you will be able to see the equivalence of two arcs. Which is the arc that he is referring to? That is something which we spent quite a bit of time to figure out. So, this to prove that, say this arc chaja is same as this jhata. So, this is what he is trying to prove here, and that by geometry one can do, but one has to do a little more carefully. So, we are able to figure that out. Okay. So, that said, I can move fast now. So, okay. So, this is how he moves on, and then so this sum of arcs is essentially this. So, we will just get this, and then so this this Shilpa Siddham, I mean I would like to admit that though we have done a lot of mathematics and so on, we could not really figure out unless we could read the later verses. So, how do you visualize this and then prove for yourself? So, some 3 more verses are there. So, Karkatakena Jatabhyam. I want to just draw your attention to a few terms here. So, this equilateral triangle, he uses the words Tulya Tribahukam. See, this is a Bahuvrihi compound. So tulyaha tribahavaha yasmin tat tulya tribahukam kritva. How do you draw this equilateral triangle? Karkatakena jatabhyam timina tulya tribahukam kritva bahiriha kone dhritva gam. So all that very detailed description where you have to choose the point and where what you have to measure, how you have to draw the arcs, and then get the say this point. See, you see timina tulyam. The word timihi in Sanskrit means in this context, many of you in Tamil Nadu timingala. Timingala means a huge what is it called? Shark whale. Yeah. So in fact, we have timihi, timangala. I found I remember this verse, I have heard this. See, astimatsyastimir tatha chasti timingilaha, timingila gilopyasti. This is basically to say people who can swallow. This timingila is a whale which can swallow many things. Somebody said there is a small fish that can be swallowed by timingila. There are people who can swallow even timingila. So that is how in that context it is used. Timingila gilopyasti. Gilaha means one who swallows. Okay, it is just to describe people. Sometimes people use this. Saha timingila gilaha, they say. He will swallow everybody. Okay. So anyway, so these are other details which we find here. So this diagram is what he is basically describing. So 3 verses. And once we draw this diagram, one can straight away see that chaja is same as jata. Okay, so that is how he describes the shilpa. And the last thing that I wanted to say is, so the sign of 1 degree. And this Nityananda, having described so all this in great detail, how to find sin theta plus phi, sin theta minus phi, all that are described very elaborately in about 30 verses, 30 plus verses. Then he moves on to this formula. I don't really know who first gave this, because trigonometry was developed in various places. I tried to search also, which I am not able to get a clear answer on who first gave this formula. But sine of 3 theta is this is 3-part formula, multiple angle formula, various things that the people say. So once we take
India who would have given, apart Kamalakara has given.
Ada, I have no idea. So I have no idea. So, but he starts with this. So we start with this formula, and the idea is to find out sin theta. Okay, sin 3 theta, this expression is known, and once you know this expression, of course, anybody who has the way to find sin of 2 theta, sin of 3 theta, he may be able to do this. Once you know sin theta plus phi, obviously one can arrive at this formula, but who first gave, we don't know. So we have clear expressions, analytic expressions for sin theta plus phi. Okay, so given that, so now we use this formula and we want to find out sin theta. Sin 3 theta value is known and you want to find out sin theta. So this is the problem that has to be handled. So you can consider this to be an equation like this. So suppose you say y is sin 3 degree, this is known to you. And then you have y cube appearing here. So you have to find out various ways to obtain y, solve this equation. This is a cubic equation to be solved. This has been attempted, yes?
Which period is this?
This is 17th century.
17th.
Yes. And here Al-Kashi around 15th century has also presented this. So his idea is, so instead of finding y, so they will find 2y because they use this chord as such. And then you have to divide the value by 2, you will get this. So how is it done? So you get an expression for 2y. So this is first hexadecimal, second hexadecimal, third hexadecimal, you go on finding so various accurate values. And this is done by a certain iterative process by how do we go about? So you just start with this and then, okay, this is the one, okay, so here I have, so we have this, you first get P naught, then you use certain procedure, you use the value of P naught, then you get P1 and then use P2 and so on and so forth. In the nth stage you will have Pn. So you can keep on doing this iterative algorithm to whichever accuracy you want, okay. So that is how he has found. That itself is a very interesting thing, I mean, a remarkable thing. I don't know how people have been having patience. So you see this is 3 degrees and then you get seconds, thirds, fourths, fifth, sixth, seventh, eighth, ninth. Okay. So they have gone on 1/60th of it, 1/60th of it, 1/60th of it, and so on up to this details. Okay. The distinction that one finds in Nityananda's work, see, after all, we all know this is something which is done in the other civilization, so Al-Kashi. And then this Muslim rulers were there, these were astronomers in the Mughal emperor's court. And therefore, they may have to look at that work and then adopt this work and then do various things. But what is interesting about Nityananda's thing that I found is, so he has described what has been done there, but then he has also given another algorithm which seems to be much more interesting. So one point which I want to draw your attention is, so here this Nityananda's work, so you find 50 which is given there and 29. So there is a distinction between the two values that are presented. Now we go here. What did Nityananda do? We don't have much time. The second method of Nityananda, so describes a slightly different way of approaching this cubic equation. What Al-Kashi did is a different kind of a thing, and what Nityananda does is a slightly different thing. So he describes another way to solve this cubic equation, and what he does is, so he just instead of trying to do this, so he just says you take the first solution to be this first value. I mean, you can ignore the y cube term, and then you just take this. So there, this is some remainder, and then you deal with that. So here you just drop this, take this, substitute back into the equation. Okay. So you have this equation basically to be solved. Y is a function, you have a y in the right hand side. So you first do this, and then you use this value y0 as the approximation, and then you get y1, and then you use y1, and then you keep on doing this. You understand? So this is how. So this is a much better approximation that you have got.
That, finding the arc.
Precisely. Exactly. That is what I wanted to say. This is something which is prevalent in our tradition, which was not present in the other tradition. But there is another advantage that we see in this approach, which is what I will show you in the next table. So you do the iterative process till yn plus 1 becomes yn. This is something which has been adopted as an iterative procedure in most of the things, in most problems in astronomy that we find. And not only in sine function, in other things also, in other ways also. Okay, so what is the interesting part about this approximation? So you see that it converges so fast, the 9th decimal place, 9th sexadecimal place, I would just say. So you just get in 5 iterations, that's it. Okay, so it is so fast converging, and in modern parlance, if one were to describe this algorithm, one can describe this to be fixed point iteration technique. So you choose some value, and then you see that it sort of very quickly converges. Okay, so that is what we find here, and this may not be described that way, but they had understood this iteration converges so fast in most cases where we have to deal with problems. Okay, that in astronomy, that is what one needs to understand. So it has been noted before that such approaches were employed by Indian astronomers in the earlier period to solve similar problems. So that is all I wanted to mention here. Okay, the last part of my presentation is just to show you how they have been presenting. So we were trying to get into the manuscript and then try to decipher, right? So how are the equations presented? So you see, so this is, we just use y. So and they use, even yesterday Amartya was doing his presentation. See, so Kalakam, Neelakam, Harikam, so all that, so we were using this, these alphabets which represent the color of certain objects, Varna, and that Varna is used to represent an algebraic variable. So here you see this bhu means base. Okay, so if you have a certain triangle and you drop something onto the base, you use the word bhu. And if the point that is denoted above is, so let us say A, and we use ya, so ya bhu, etc. Those kinds of things we will use even in the description of diagrams. So here you find b minus y. Okay, so this 1 to the side of it represents the coefficient of the variable. Okay, the coefficient of the variable, and bhu again coefficient, both are having 1, 1, therefore you have 1 here, and b minus y. So divided by 2, you will see something slightly in a lower sized font, because they cannot afford to give one more line while writing in the manuscript. So they will just put it slightly above and slightly below, they will put this. So this is how it will appear. So a little more complicated expression you find here. So what you find here is, see, this 3 basically represents the coefficient 3, the number 3 here, and then you see this va represents the varga. So y square is ya varga and the coefficient is 3, and then you find 2by, b is used for bhumi, and again this variable comes and the coefficient is 2, and then you find this the dot will be there above 1, so that is the notation that is employed to denote it to be negative. Okay, so a negative coefficient so is usually denoted by a dot in the coefficient. That is how
Variable you are using the ukara, that is rare, right?
where
Ya, ka, bha, nu, those are the
no, where do you find u?
bhu.
Bhu. So because he has to describe in that, so bhu he uses. Correct.
At the base of the quadrilateral.
Base of the quadrant. Yeah. So do we find bhu?
Length of the
Length is also correct. Bhu is used to refer to the bhumi. Yeah, bhumi. I think it could refer to the bhumi itself, the whole length. Maybe I am mistaken. I just so that is how it is. Okay. So you can see how this is one of the very well written manuscripts. So where you find, yeah, it's a nice handwriting where you find a nice, but there are so many manuscripts which even Clemency was showing earlier. So they would just go like this. So that depends on the scribe and the amount of time that is spent in trying to do this. The concluding remarks. So Nityananda provides a very detailed and systematic exposition to the sign, the whole rationale behind obtaining the sign values. So this kind of a detailed picture we don't find in the earlier works as far as we know. All Bhaskara of course has devoted a chapter to exclusively for the sign function, which is called Jyotpatti in the Siddhanta Shiromani, but we do not find this detailed description. There are about 65 verses in this Nityananda's work. He provides a beautiful summary of Alkashi's method, but silently presents another way of solving the cubic, which is typically the Indian approach. The geometrical construction described for getting the this I did not I cut in my slides. So this is another thing. So how to get this sine 3 theta formula? Okay, he presents a nice geometrical approach. There are a few verses devoted to that, and based on that you move further. Okay, once you have sine 3 theta is equal to sine theta and sine cube theta, etc. So for that, how do you get that? He provides a very nice simple geometrical construction. So interestingly, the new method given by Nityananda fetches the value of sine of 1 degree in 5 iterations, in contrast to the 10 steps, that is far more involved computation, which you find in Alkashi's method. The numerical computations of Nityananda's method are simpler, whereas Alkashi's method are far more complex and involved. Thank you.
Thank you, sir. We now have the presentation on reasoning methods, upapatti, and expository techniques and commentaries by Professor Mahesh K. Professor Mahesh is working at the Center for Excellence for Indian Knowledge Systems at IIT Kharagpur. He did his PhD from IIT Bombay and his postdoctoral research at CNRS, France. His published extensively in mathematics and astronomy, and including the volume Studies in Indian Mathematics and Astronomy, which he co-edited, and the astronomical text Karanabharana, also co-edited. In 2015, he received the Young Historian of Science Award from the Indian National Science Academy.
Shri Gurubhyo Namaha. I seek blessings from my Guru and Param Gurus, from whom I acquired some knowledge about this, which I am going to present today. Shri Gurubhyo Namaha. Drangna Sukti Mucham Vyanaktu Sagiram Girvana Vandyo Ravihi. So when we consider this Indian astronomical literature and mathematical literature in India, so there are two types of texts, which are called Mula Grantha and the Bhashyas or Tikas. Mula Grantha means the source texts, like the texts written by Aryabhata, Brahmagupta, Vrahamihira, and so on. And there are several commentaries on these source texts, which are called Tikas, Bhashyas, or Vivritis, Vivarana, and so on. So the original source texts, they are presented in a brief manner. They are concise in their presentations. So whereas the commentaries help us in understanding the methods presented by those astronomers in a better way. The Aryabhatiya, so which was written in 5th century AD, this is the one of the earliest texts which is available today in the Siddhantic astronomy. And so we have Aryabhata, Varahamihira, Bhaskara the first, then Brahmagupta, and so on, so have written these source texts. And we have the commentators like Prithudaka, Bhattotpala, Parameshwara, and so on. So this is the list of various astronomers and mathematicians, and the texts which are.
Brahmagupta's birth and death year, they explicitly mention in the text?
It is inferred. It is inferred actually. So from the Karna text, so which was composed later. So.
Why are you referring to Bhaskara as last of the celebrated astronomers?
No. So see. Much. Huh?
The last of the celebrated.
That was earlier notion.
so then we have the list of Kerala School of Astronomy and so on. So in this list, many of the names are, which are discussed in mainstream academia. So, but very little work has been done on these four topics actually. The methodological foundations of Indian mathematics and understanding the nature of mathematical objects, the nature of mathematical knowledge, and the methods of validation of mathematical results and processes. So in this context, we need the help of the commentaries. There we feel the role of commentaries, so which are called Vyakhyas and Bhashyas. So the commentaries provide various ways to arrive at the formulae discussed by the earlier mathematicians and astronomers. So when we look at Aryabhatiya, so these are the various commentaries available. These are the names of the commentators who have commented on Aryabhatiya. So Aryabhatiya was a popular text in India. So in different regions of India, the tradition of Aryabhata grew later. So some of the commentaries are available to us. And when it comes to the case of Leelavati, more than a dozen commentaries we can see. So among those commentaries, the Ganesha Devajna's commentary, which is called Buddhivilasini, and Kriyakramakari of Shankara and Narayana, and Nisrishtartha Duti of Munishwara. So these are three major commentaries So among them, this Nisrishtarthaduti is praised as the Uttamottama, the excellent among those best commentaries.
And that is what was released.
Yes, yesterday, so we have published that. And so we need the help of these commentaries to counter this widespread belief that so Indian mathematicians did not present any proofs for their results. That is what we find in the works of writings of Maurice Klein, C.B. Boyer, and our own 9th grade textbook. So where it is said that Hindus apparently were attracted by the arithmetical and computational aspects of mathematics rather than by the geometrical and rational features of the subject. So
asking which edition of NCERT.
So perhaps now it got changed, I think, in the recent edition.
New edition hasn't come up.
Not yet come up. So work is going on. Yes, yes,
Work in progress.
yes. So the notion of upapatti or the proof in Indian tradition is quite different from this Western that of Western tradition of mathematics. It is not if it does not really depend on this proof by contradiction or reductio ad absurdum. The purpose of upapatti in Indian tradition is considered to remove the doubts and confusion in one's own mind and to present it in the assembly of scholars. So this is what Narasimha Devajna says in his Vasana Vartika, Panditya and Brahma Nivarana. So the word yukti or upapatti, so yukti means a connection, so it is a logical connection between the result and the rationale. So upapatti means moving closer towards the understanding the results or the to arriving at the truth. So these upapattis can be of various types. It can derive the algorithms or justifying the astronomical models or demonstrating consistency with the observation, that druktulyata, what it is called, and providing intelligible rationales for approximation or computational shortcuts. So this is what Bhaskaracharya says in his Siddhanta Shiromani. Madhyadyam dyusadam yadatra ganitam tasyopapattim vina praudhim praudhasabha sunaiti ganakaha nissamshayo nasvayam. It shall neither be possible for an astronomer to assert his views convincingly before an assembly of scholars without a proper exposition of the underlying rationale of the computation of mean planets and so on. So it shows the importance of upapatti or the proof in the Indian tradition. So in the Indian tradition, these pratyaksha, anumana, upamana and shabda, all the four means of cognitions are taken as the valid upapattis. So when it is about the authentic tradition, the words of the previous scholars are not enough. So Bhaskaracharya says, Ganitaskandhe upapattiman agamah eva pramanam. Upapatti, that though these things are enunciated in the authoritative text, it cannot be accepted unless it is supported by an upapatti. So this was the importance given for the upapatti in mathematical tradition. This is the planetary model. So all astronomical texts described. So where various conceptual tools are taken for presenting the true motion of the planets, like Ucha, Nicha, Madhyama, Shigra Paridhi and so on. These are actually the fictitious tools, so by means of which we derive the true position of the planet. So in Indian tradition, a model can be fictitious, but it can lead to the right knowledge. This is the ontology of in the Indian context. So when now let us look into some upapattis described in various commentaries. So this is the sum of squares and differences of the squares described by Bhaskara in his Lilavati. So Rashyor Antaravargena Dvigdhegate Yutetayo and so on. So Ganesha Devajna in his Buddhi Vilasini, he gives the upapatti for this. So this is a square plus b square is presented using these four right angle triangles, and he explains how those have to be placed in order to get a bigger square, and how the hypotenuse can be computed. So tresra samanyeva chatvari tresrani parivartya karnam bhujasthane nyasya and so on. He describes it. So and then he says in the middle we have a smaller square which will be equal to a minus b. So and the sum of the areas of the triangles and the inverse square will give the area of the derived square. And for the difference of squares, he shows it like this. So you have to take 5 by 5 square and remove 3 by 3 square from that, and whatever the remaining unit squares we have in the resulting figure, you have to arrange it in such a way to get a rectangle which will have the sides equal to a minus b and a plus b. He demonstrates it with these numbers 5, 3 and the 5 plus 3 and 5 minus 3. So when it comes to the algorithm for squaring, this is the verse of Bhaskaracharya we find in Lilavati. It says the first phrase gives the definition of a square. Samadvighatah kritihi, the product of two equal quantities gives you the square. The word kriti refers to the square here. And then in the rest of the verse, the procedure is described. Sthapyontyavrago dvigunantyanignaha swaswo parishtacha tatha parenkaha tyaktvantyamutsaarya punascha rashim. So let me explain it using an example. So here the number 297. So where this 297 can be taken as A, B, C, and so above the last significant digit, you have to place the square of that. This is called A square, Ya Varga, and then we place 2AB above the digit B, that is called Ya Ka multiplied by 2, and then 2AC is placed, and then we drop the last digit and slide the number. Then we place this B square above 9, and then 2BC and C square, and if there are more digits we have to repeat Punascha Rashim and Tyaktva Antyam. So once the operations with that particular digit is over, we have to omit that and slide the number, and we have to continue the process. So this is the algorithm presented by the stepwise method presented by Bhaskara, and from the time of Aryabhata itself it was known. So later commentators explain it in detail. How does this work? This is the Buddhivilasini explanation for this. So here he uses this algebraic way, Ya Ka Ni, A plus B plus C whole square, this Ya Varga, so the Bhavita of 2 Ya Ka and so on. So he says Pratamasthane Antyavargaha, in the first place you have the square of the last digit, and in the second place the product of two digits, two variables and the twice of that, and so on. So in the Munishwara's commentary, we see, so how does this work? He says why the square of the digit has to be placed in the leftmost place and so on. This is the pros related to that, and this is how it can be shown. So I will not explain it in detail. And there is a square root method given by Aryabhata, and this is the verse from Lilavati. So where he says he uses the reverse method of a plus b plus c whole square, so where we the digits are grouped like marked like Vishama, Sama, odd, even, and so on. From the last Vishama place, we subtract a square, the maximum square which can be subtracted, that is marked as a square. So then twice the a will be the divisor for the next step, and whatever quotient we get is taken as b. So then the sum of this 2a and 2b will be the next divisor in the next step. Then we get c as the quotient in the next step. Then we subtract c square. This 7 square is subtracted. So this is how we get use the reverse algorithm of the squaring in extracting the square root. So this also is explained nicely. How does this work? So the Munishwara explains it in his Nisrishtartha Duti like this. So varganke ekadisthanani vargasthanatvena vishama samattarupena ankitani. We have to mark the digits in the given number like Vishama, Sama, and so on. And from the last digit it has to be subtracted, and so on. A detailed explanation is given in the commentary. So similarly, we find the cube root method. So where we subtract a cube in the beginning, then 3a square b and 3ab square and b cube, and so on. So this is the algorithm presented by Aryabhata. This is how we extract the cube root. So in the commentary of Aryabhatiya by Nilakantha, the Aryabhatiya Bhashya, so where Nilakantha shows his inclination towards geometrical description of explanation of any mathematical proof. So he says tadyuktirapi mrudadina pradarshya, either by using the model of clay or model made by wood. So we have to show this to the benefit of the students, or the kshetra kalpanayapi pradarshya, using some geometrical construction it has to be demonstrated. This is what he explains. So let us see one example from Aryabhatiya Bhashya where he presents this the ghana.
The term Mridadina should be understood as small cubes.
Mrit, made by mrit,
Small cubes.
made by clay.
Rather, Kshetra is by
Drawing diagrams. So this Mridadina, or this using wooden cube, he explains, he gives this the expansion of a plus b whole cube. He says that there are 8 parts, like two cubes like a cube and b cube, and 3a square b's and 3ab squares. So in total we have 8 parts. So this has to be demonstrated by cutting a cube. So this is how he says. So you have to draw east-west line, and the Yamyottara, this northwest, north-south line, and there is a third way of cutting. So in 3 ways, so we have to dissect the cube, and then you get 8 parts of the cube. This is the geometrical description given by in the prose form. We have drawn the diagram for that based on the description. He says where it has to be marked like A is to B and so on.
Bring them and demonstrate it too.
Yes. So this is how he says. So when you cut the cube like this, we will have 2 samad dwadashashra. Dwadashashra refers to a cube. So one will be a smaller one, and another one is bigger than that. So those are shown in the colors here. So, and he says the adjacent cubes, how they would look like, and what would be their direction, what would be the adjacent side, with the touching with these 2 cubes. So there is a nice description about that. This is how he describes it. And finally he says this is how we get the cube of 9 by cutting it into, dividing it into 4 plus 5 whole cube. So this is a nice graphical description of that. And when it comes to summation, so this is the beautiful verse presented by Bhaskaracharya in his Leelavati. He says, Saika padagna padardha mathaika dyanka yutih kila sankalitakya. The sum of natural numbers starting from 1 to n is presented as Saika padagna padardha. Pada means number of terms. So that is n. Saika pada is n plus 1. Saika pada is n plus 1. Padardha is n by 2. So the product, this is called Ankayuti, sum of natural numbers. This is called Sankalita. And sum of summations like 1 plus 2 plus and 1 plus 2 plus 3 and so on. So the sum of numbers should be multiplied by Dviyuta pada. Sa Dviyutena padena. N plus 2 should be the multiplier. And in the denominator we have 3. Trihruta. Kalu Sankalitaikya. This is named as Sankalitaikya. So sum of summations. So there is a nice proof given by Lakshmi Dasa. This is quoted by Munishwara in his text. So where he says in the first row we have n square. When n's are placed in n places, padasya vargaha padamita sthanastha padankanam yogaha. If you place n in n places, the sum of them will be n square. And in the second line we are placing 1 to n minus 1 in the reverse order. That will give you sum of n minus 1 terms. The difference of them will give you the sum of n terms. So now just by taking the sum of the third row and second row, you get the first row. So that is what sum of n terms plus sum of n minus 1 terms will give you n square. Add n to both sides and just rearrange them, then you will get n into n plus 1 by 2. This has been explained in this prose. So we don't get the work of Lakshmi Dasa, but here this has been cited by Munishwara. So that is how we came to know about the Lakshmi Dasa's proof. This is the proof for Sankalitaikya. So where we have, so the series presented like this. In the first row we have 1 term, 2 terms, 3 terms and so on. So now if you look at column wise and take the sum of all the numbers in each column. So we have n times 1, n minus 1 times 2, n minus 2 times 3 and so on. And then rearranging the terms, taking n outside and we rearrange the numbers. So that is how it has been described. I will not get into the details of that. So then this Vn refers to the Vara Sankalita, that is Sankalitaikya, so sum of summations. That is how we derive the expression for the sum of summations. This is also explained in a beautiful prose by Munishwara in his text. So then there is a the same thing is called Chitighana, so sum of summations. So Aryabhatiya Bhashya by Nilakantha gives a nice description of this. So here this sum of summations is presented like this: n into n plus 1 into n plus 2 divided by 6. Now Nilakantha says take the 6 to the left hand side, then you have 6 times summations, sum of summations. This looks like a volume of a cuboid. So with the dimension n plus 1 and n plus 2. So now we need to construct a cuboid having these dimensions. So for that he says takes 6 Shredhi Kshetras. Here Shredhi Kshetra means ladder like structure. So the some arithmetic progression can be shown like a step like structure. So take such 6 Kshetras. So then you combine two of them, then you will get with unit thickness, then you will get a rectangular slab. So such three rectangular slabs you get for each Shredhi Kshetra. So such n slabs you will get. Then you have to arrange them in such a way to get a cuboid. So the first layer, so first set of layer will in the bottom and vertical to that and the perpendicular to the vertical. So this is how you get. And the next step, n-1 the slab, so you will place it in interior sides. So this is how the final cuboid will look like. So the volume of this n into n plus 1 into n plus 2 will give the 6 times the sum of summations. You divide it by 6, that is how you derive the. So the physical significance of the formula is presented in a nice manner. This we find in the text of Nilakantha Somyaji, so which is called Aryabhatiya Bhashya. And this Makhi Bhaki table, so this by the Jya table by Aryabhata, this has been used extensively in some other computations. So just I will show one proof for the surface area of a sphere presented by Bhaskaracharya in his auto commentary called Vasana Bhashya in his on his Siddhanta Shiromani, where he describes two proofs for obtaining this the surface area of a sphere, which he calls it as Vyasa Paridhigata, product of the circumference and diameter. Instead of 4 pi r square, he says it is the product of C into D. So he uses two methods. The one is trapezium method and Loon's method. So in the trapezium method, he says you have to cut the hemisphere into several annular strips and cut that the annular strips and flatten them. So then you get trapezium. So you know the base and face of the trapezium because you know the circumference of the those circles, the great circle and the small circles, and you know the altitude because you know the difference between the successive arc bits. So that is we are making 24 segments of the hemisphere. That is why we know the altitude. It is 225 arc minutes. And then using the Jya table, you can simplify that formula. So that is how you get the surface area of the hemisphere. Twice of that will be the surface area of the whole sphere. So that will be equal to the product of circumference and diameter. This. So that is how he compares the formula with the computation. This is how he validates his formula expression given for the surface area of a sphere. So here a curvilinear figure is cut into various small rectilinear figures. So then by summing them up, you get the total area. This is the idea. So these are the proofs which really help us in understanding the nature of mathematical the presentation of mathematical objects. And so the various discussions really help us in understanding the nature of upapattis, etc. And these upapattis may greatly help us in the modern pedagogy also. So that is why, so studying about this ancient Indian mathematics, it is not just about the study of the past. It may help us in, it would certainly help us in going further also. So that is what I wanted to present. Thank you very much.
Thank you so much. We now have a tea break. The tea is served in the terrace pergola outside, and we reconvene at 12 noon for the next two speakers.